Okay, so this is the first podcast in our nuclear chemistry unit, and we are going to cover isotopes.
And we've already reviewed those a little bit way back in Chapter 2, but we're talking about nuclear chemistry, and isotopes is a big part of that.
There's some pictures here of things that use isotopes. Nuclear medicine is one of them. Radiocarbon dating, which tells us how old things like fossils are and artifacts and all that kind of stuff. Paleontologists might use that.
So you can use isotopes for medical x-rays. They light up different parts of your body, kind of like Homer Simpson does in this next clip here.
Now, what you see here is the radioactive dye we injected flowing through your husband's circulatory system.
But, Doctor, I haven't injected the dye yet.
Good Lord. Hi.
Quick review for isotopes, or for just in general the atom. Protons, they identify an element. That's the atomic number on the periodic table. That will never, ever change. An element is identified by the number of protons.
Neutrons, however, they can change. Different numbers of neutrons give the element different atomic masses.
And that's actually what we're going to be talking about with isotopes, is the different types of masses that elements have. And then electrons, again, review, they can change. If you have more electrons than protons, you get negative. If you have less electrons, it's positive. Those affect the charge.
So we've talked about electrons and protons and compared them in some pretty good detail. Isotopes, we're more going to talk about the neutrons more than anything.
Here's a definition of isotopes. It's atoms that have they're the same element.
So they have the same number of protons.
Same number of protons because they have the same element. But there are a different number of neutrons, which gives a different mass.
All right.
Quick example of that is, you may have heard of carbon-14.
That's the one that we use for radio dating that I was talking about.
It identifies fossils and things like that and tells you how old they are. But it's just another form of carbon, and they can be written, that 14 there is a mass, versus carbon-12, which is a normal carbon, and that's the one that's on your periodic table. So both of those numbers there are masses, where carbon can have two different masses because they're two different isotopes, but they're both carbon.
Interesting note, we all have carbon in us. It's carbon-based life, if you ever heard of that term. We actually all have radioactive carbon inside of us, just very small amounts. So we all have that carbon-14. And when a living creature dies and isn't living anymore, the carbon-14 starts to decay, and you can actually measure how much of it's there over time, how much of it is gone. Anyway, that's carbon dating.
That's how you do carbon dating.
Yeah.
Notation, very important for this chapter. Let's take strontium-90, so strontium with a mass of 90, and we're going to make this one an ion just so you can see the charge. Start out with the basics.
Strontium's symbol is Sr. Find that on the periodic table.
That's useful.
Yeah.
The 90 is the mass.
Okay, the 90 is the mass.
And
Good.
the mass gets written in the upper left corner of the element symbol.
All right, so all strontium atoms have a mass of 90, right?
No, just this one isotope has
okay.
a mass of 90.
Oh, that's good to know.
Not all of them. That number can change.
Okay.
This number's not going to change, though. All
This is the one
strontiums have 32 protons.
All right. Good.
And since we know this one's an ion, you can look up in the periodic table, and it is in the positive 2 column. So since this one says it's an ion, if you need it, it has a charge of +2.
Okay, so strontiums all have to have that atomic number 32. They have 32 protons.
Check.
Great. Electrons, there is a charge of +2, which means we have 2 less electrons than we do protons,
Because it's
giving
positive.
us 30.
So we've got 2 less of them.
Now the mass, this is the hard part.
The neutrons here change with the mass. In this particular atom of strontium, the mass, this is a good time to write down if you forgot, the mass is made up of the protons plus the neutrons.
So it's really not that hard to calculate. I was just kind of...
A quick subtraction
little
problem.
goofy.
90 is the total mass. 32 is the protons. So subtract 90 and 32 and you get
Yeah, no big deal.
58 neutrons.
58 neutrons.
Pretty straightforward. Isotope notation. You're going to see a lot of that. The mass always is written in the top left. The atomic number in the bottom left. You kind of saw us write it like this, where you can write the element name and the mass.
Yeah, carbon-14, carbon-12.
We can shorten it even more with the element symbol.
Yeah, still with its mass.
Still with the mass, because you have to tell the mass,
Yeah.
so you know which version of carbon you're talking about.
Right, that helps us identify the isotope. And then there's the symbol in the full isotope notation, which shows the mass number and the atomic number on the bottom. Both have 6 protons.
because they're both carbons, so 6 is good. That identifies it.
All carbons in the universe, no matter where you find them, even at the farthest reaches of the universe, if you find a carbon atom there, 6 protons.
Always, always, always. Neither of those notations have a charge, so they also both have 6 electrons, because they're neutral.
Uncharged particles, equal number of protons and electrons.
But their masses are different. The one on the left has a mass of 14, which means it has a different number of neutrons. 6 of that mass come from the protons, which means 8 neutrons.
All right, and then the one on the right has a mass number of 12, and 6 of the mass comes from the protons, so that means there are 6 neutrons.
Okay, so the neutrons change, and that's what's responsible for giving you the different masses of the isotopes. You might notice, though, that the masses on the periodic table are decimals. They're not whole numbers like these isotopes. They are actually a weighted average based on the abundance of how often the isotopes occur in nature.
Oh, so that's why they're not whole numbers. That makes a little bit more sense now.
Because it's an average.
Yeah.
But not a normal average, a weighted average. For example, if we had those two isotopes we're just talking about, carbon-12 and carbon-14, if I took the average of those masses, I would get
13.
13 right in the middle. But that is not a weighted average. That is a normal average where you take, you just add them up and divide by the total. So 14 plus 12 divided by 2, you get 13 as the average. If you look on the periodic table, though, carbon has a weighted average of 12.01.
Yeah, so its average atomic mass, 12.01. That means it looks to me it's closer to 12, right?
It's closer to 12.
So there's more carbon-12 than there is carbon-14 in the universe.
So there's a lot more. Almost 99% of it seems to be carbon-12 to get the average close to 12. You already know what this means, and you know how to do it if you've ever calculated your grade. Because you have a first quarter grade, a second quarter grade, and an exam grade, and those grades have different weights. You don't add them up and divide by 3. You take 40% from your first quarter, 40% from your second quarter, and 85% from your exam. I'm sorry, 20% from your exam.
The exam was an 85, though.
Decent score.
Yeah.
So you already know how to do this calculation. Let's walk through it real quick on how to do a weighted average. So I don't want the 40%, I just want the decimal. I'm going to say 0.4.
Well, we always use the decimal of a percentage when you're doing calculations with percentages.
40%.
Yeah, so 0.4, 40%.
So 40% of my 88.94, that's my first quarter grade. And I'm going to add that to the 40%, which is a 0.4, of my second quarter grade of 94.12. And I'm going to add that to my 20%, because your exam grade counts for 20%. That 85 you got doesn't go as far as the 88 or the 90, but it's still 20% of your grade. You can add those up and take a weighted average. Each one counts for a different amount. And you get a score of 90.3% for the semester. Not too bad. You're barely squeaking out with an A-.
Right, so to summarize weighted average, we're taking the decimal of the percentage, not the actual percentage, but the decimal of the percentage, so the 0.4, 0.4, and the 0.2, and then multiplying that by, in this case, whatever the grade was, in the percentage of the grade. With the isotopes, we're actually going to multiply the decimal of the percent by the mass number.
Let's take a look at that. Same thing here with isotopes. They have different abundances. Here's two isotopes of copper. Copper-63.
Which actually has a mass of 62.93, but pretty close to 63.
It's close to 63. So. This is the one we're going to use, though, because it's a little more exact. And it has an abundance of 69.1. And copper-65 has an abundance of 30.9%. So since there's more copper-63 in the universe, the mass, or the average, is going to be closer to that number than it will to 65.
Okay.
Because it's a weighted average.
That makes sense.
So let's take the mass of those. I want my 0.691% of the copper-63.
Remember, the decimal of the percent, all you do to get that is divide by 100. Easy.
Multiply that by the grams. This is my copper-63. That's the weight from that. And I'm going to add it to the percent, 30.9 in decimal form, times the mass in grams. I'm going to add that to my copper 65 weight, which is 30% of that one. I get those together, and I will get an average atomic mass of copper. This is why they're averages on the periodic table, of 63.55 grams.
So this is the number you're actually seeing on the periodic table, the 63.55 grams.
Coming from the average of the two isotopes,
Yep.
the weighted average.